Today I'm going to be completing part C of homework 1 for process dynamics and controls. Now to get started here, I'm going to do a brief overview of our question. So we've got a continuously stirred tank with an inlet volumetric flow rate of Qn, an inlet concentration of CAn, and an inlet temperature of Tn. Inside the bulk of our CSTR, we've got a volume V derived by taking the area times the height, the concentration of Ca, and a temperature of T. And being that this is a CSTR, our outlet concentration and temperature are going to be the same as our bulk concentration and temperature with a volumetric flow rate of Q out. Surrounding our CSTR, we've got a cooling water jacket that stays at a constant temperature of Tc, as we're going to assume that the jacket is well mixed. Alright, now that we've got our problem modeled and set up here, we're going to go ahead and move in to finding our time-dependent material balance. And to do this, we need to find our moles in per time. To do that, we need to take our ECA H times our area. As this is our height times our area, which is our volume, times our concentration, giving us our moles over our change in time. And this is just going to equal our inlet concentration, CAN, times our inlet flow rate, QN, minus our outlet concentration, Ca, times our outlet flow rate, Q out. Alright, so moving on from here, we're going to need to separate out this variable as we have two time-dependent variables here, and we're going to do that using the product rule, which is going to give us H times dCA dt plus Ca times dH dt equals our CAN, QN, Ca, Q out. So from here, we need to go ahead and isolate this variable right here, our change in concentration over time. So to do that, we're going to do dCA dt. This is all divided by the area, by the way. Forgot that up here. It's going to equal 1 over A times CAN QN plus minus CA Q out. This is all going to be subtracted by Ca times dH dt, all times 1 over H. So what can we do from here? Well, let's pull from a couple equations we figured out earlier in previous parts. So we know that dH dt equals 1 over A times Qn minus Q out. Which is going to be very helpful that we can sub this in for this. The only other thing that's pertinent here is that our volume is actually going to equal our area times our height. And these two equations allow us to rearrange everything here to get dCA dt equals our Qn over our V, as we've got here we've got 1 over A, here we've got 1 over A. We move them both over, we get 1 over H times A, which is just going to be our volume. And then we can also take from this equation and this equation, we can pull our Qn out, putting that above. And all that leaves us with is our CAN minus our CA. As we can completely eliminate our Q out by again subbing in this equation. Now it's not this simple, as we've got a reaction going on here. So another important thing we need to add to this material balance is Rk, which is our reaction rate constant, times our Ca. Where are we going to get that K? Another pertinent equation we're going to use is the Arrhenius equation, which says that K is going to equal K naught times E power our activation energy over RT. This equation is going to become pertinent later when we move into Python. But now we have one equation that we're going to need, and our time-dependent material balance, our dCA dt equals Qn over V times Ca in minus Ca plus Kca, our reaction. Alrighty, and now we're good to go ahead and move on to our energy balance. Alright, now that we've got our time-dependent material balance and our Arrhenius equation, we only need one last piece of this puzzle before we can move into Python and simulate this as CSTR. And that's going to be our energy balance. So how are we going to get our energy balance? Well, first, we know what's changing. It is our temperature, as this is an exothermic reaction. But an energy balance is in units of joules per second, not in units of kelvins per second. So how are we going to get to joules per second? Well, we're going to need our heat capacity, which has units of joules per kilograms Kelvin. So we'll go ahead and multiply the left-hand side of our equation by RC. What else are we going to need here? Well, now that we've got kilograms in the denominator, we're also going to need to multiply by our density and our volume, all of which are staying constant here. So now that we've got the left-hand side of our equation in joules per second, let's focus on the right-hand side. So the first thing we're going to take a look at is our temperature in minus our bulk temperature. Obviously, this is also in units of Kelvin. So to get it into the units we need, we are again going to multiply by our C, as well as our Q in, our volumetric flow rate in, times our density to get us into units of joules per second. From here, we've also got the heat transfer from our cooling jacket pulling energy out of our CSTR. So since we're pulling energy out, we're going to do a minus our heat transfer coefficient, because we don't have all day. We're not going to derive the heat transfer of this. We're just going to hand wave it with our U, times the area, surface area of our CSTR, times our temperature minus the temperature of our cooling jacket. Now there's one more variable to our energy balance that we need to take into account, and that is, of course, the heat generated by our exothermic reaction. And to get that, we're going to go ahead and add minus delta H of reaction, as this is an exothermic reaction, times our rate constant times Ca from up here. But up here, we divided by volume. On here, we have volume on the left-hand side of our equation, so we also need to multiply by the volume. And here, we've got our dynamical, time-dependent energy balance, which is the last piece of the puzzle to model this CSTR. So now we're going to go ahead and move into Python. Alrighty, I'm going to go ahead and get started with the Python section of our video on Homework 1, Part C. So as you can see here, I've done all of our prerequisites. I've imported our numpy as NP, imported our solve IVP, and imported our make subplots. As usual, we're going to need to solve our problem and make our plot to get paid. I've also this time around taken the liberty of going ahead and putting in all of our values we're going to need, because you guys don't need to watch me type out all these values as we have in previous videos. I think we're good to just go ahead and copy and paste this from the question. So we'll go ahead and move on to solving this problem. All right, so we're going to go ahead and define our right-hand side as a function of time and a vector, as usual. From there, we're going to define our vector as a CA and T. Moving on from there, we are going to go ahead and put in our erroneous equation. So K equals K naught times NP dot EXP negative ER over T. And moving on from this, we're going to go ahead and define our material balance. Our DCA is going to equal our Q times our CAN minus CA all over V. And then we're going to go ahead and add our reaction. So our K times our CA. And that's our material balance. Moving on from that, let's do our energy balance. Our DT is going to equal our Q times our Tn minus T. And since we went ahead and moved the rho, C, and V over to the right-hand side, we're going to go ahead and divide this by V times rho. Moving on from there, we are going to go ahead and add our heat transfer. So that's going to be our UA times our T minus UA, I should say, times our T minus our TC, all divided by those constants that used to be on our right-hand side, our rho times our C times our V. Perfect. And then to that, we're going to go ahead and add our heat of reaction, which is our neg HR times our K times our CA, all divided by rho times C, as we had V over here before we divided by the constants on the left-hand side. And that's our energy balance. Moving on from there, we're going to go ahead and return our DCA and our DT. Alrighty, so there's actually a couple mistakes in this right-hand side down here. I need to go ahead and remove our rho there. Have it just be V, then we are subtracting this variable. Alrighty, now I can go ahead and solve our IVP. So to begin that, we're going to say our end time equals 10 seconds. And then we're going to define our t-plot as np.linspace from 0 to our end time. And we'll put 500 points in between. Why not? Moving on from this, we can go ahead and solve our IVP. So we're going to say our result equals solve IVP of our right-hand side, going from 0 to our end time. We're going to have our starting variables be our CA naught and our T naught. And then our method, as usual, is going to be our Radow method. And we're going to set our dense outputs to be true. Fantastic. Moving on from there, we can go ahead and call our CA plot and our T plot the solution of this solve IVP based off of our t-plot. Looks like that all worked. So we are good to go ahead and get our plot and our pay. So we're going to have figure equals make subplots. This time around, we're going to have rows equals 1 and columns equals 2 because we're having two different plots on one figure. To this, we're going to do figure dot add scatter and have our x variable equal our time. So our t plot, our y is going to be our CA plot. We're going to do lines as our mode, have our row equals 1, our call equals 1, and we're going to have the name ERCA. And then we're going to do figure dot add scatter. Our x is going to equal our t plot. Our y is going to equal our big t plot for our temperature. Our mode is going to be lines yet again. Our row is going to be 1. Our column is going to be 2 this time around. And our name is just going to be t. Enter. And then finally, we're going to update our layout as usual. So update layout. We're going to do our width. Actually, you know what? We can do Plotly Light today. Let's just see what our figure looks like. Shift enter. Beautiful. So as you can see, as our concentration decreases, our temperature skyrockets as the reaction happens, causing our concentration to go way back down. And these two, they're reciprocals of each other. As you can see, as temperature goes up, the reaction goes up, concentration of A goes down. And same with the temperature. As the reaction rate goes down, the temperature goes down as there's not as much exothermic energy coming out. So this plot makes perfect sense. And I believe that is the end of homework 1.